Hello, welcome to this virtual lecture, um, the first for this class, Land Use and Environmental Modeling, here in the City Planning / Urban Spatial Analytics programs at the University of Pennsylvania. My name is Ken Stife, and I'm going to introduce you today to the idea or the concept of agent-based modeling, and in particular, we'll focus on agent-based modeling for urban systems in urban contexts. We are living in a strange time, obviously, right now. And some of you may have seen some agent-based modeling in this data visualization put together by the Washington Post. The plot on the left shows these strange entities, these dots or beings, interacting with one another and transmitting COVID-19 without social distancing, whereas the simulation on the right is the opposite. Here you have agents or entities moving around and with social distancing. And you can see that the infection rates over time are much smaller when we practice social distancing. This is a strange kind of model. We haven't seen this model in the class so far. We'll talk about and return to the concept of bottom-up versus top-down modeling, but it's clear that there's no regression being run here. This is something totally new and different, and this is agent-based modeling, which is a kind of simulation, and that's what we're going to talk about today. We will, in fact, spend some time talking about disease transmission, although a very special instance of disease transmission, specifically around zombies, but you'll see that example fits very well in this example here. And we'll talk about planning and public policy use cases where this kind of modeling is really important. So what is agent-based modeling? This is a definition from Mike Batty. Agents are objects that do not have fixed locations, but act and interact with one another as well as the environment in which they exist according to some purpose. It's a great definition. The way that I think about it is this idea that we have agents and we give them simple rules for interacting with themselves and the environment around them. These autonomous agents then go about interacting with themselves and their environment. And what we hope is that those interactions give rise to some complex emergent phenomena. And for me, one of the most interesting complex emergent phenomena that mankind has ever created is cities, right? Cities are not, development patterns are not random in nature. People choose to locate together, land uses choose to locate together, and that leads to all these interesting feedback or externality effects that give rise to places and to cities. And so my interest has been to see how this kind of simulation, given these autonomous agents, can make us smarter about cities and perhaps interventions in cities. So the reason why we want to, we'll talk about these, this is what we're going to do today. So we'll talk about why it is that, why we would choose agent-based modeling as opposed to the other kinds of modeling frameworks that we've learned during our time together. I will demonstrate some of urban models. The first one around segregation is a very famous agent-based model developed by Thomas Schelling, and then I'll show you three more that I think have relevance in urban systems. Finally, I will show you some a demonstration using NetLogo, which is the software we'll use to build these models. And finally, I'll talk about the assignment for this module. All right, so in the beginning of this semester, I try to motivate the kind of work, the kind of models that we would be building by placing them into two categories, top down and bottom up. And if you remember, top down is really typically about regression modeling, where we start with an outcome of interest. And then we locate a series of independent variables or features to predict or explain that outcome. And a regression framework gives us the opportunity to estimate the relationship or the rules between those independent variables and that outcome. And finally, we can test empirically through all of the different goodness of fit measures that we've discussed, how well those features help to predict the outcome of interest. Now, what's interesting about this is that particularly where we have this emergent phenomenon like disease and disease transmission, that there really isn't an outcome to start with. The idea is that we're going to grow this outcome in a petri dish. And that's really the bottom-up approach that we're going to take. Um, we're going to start with these agents. We're going to give them their rules. We'll have some sort of environment. And then we'll press play and we'll watch the complex emergence occur. We'll watch these interactions grow out of nothing. And we don't, because again, we don't have an outcome to start with. We really can't test whatever the system predicts against what actually happens. So it's a little less clear how we gauge the usefulness or the accuracy, what have you, of these algorithms. But anecdotally, we can look and see, like, does this outcome conform with our preconceived notions about these behaviors? Does it seem like the simulation can be a useful planning tool? The way that I first heard about this kind of modeling was from this book in the mid 90s, where the author really grows social and economic systems, as I said, in a petri dish. He refers to it as the sugarscape. And it really was quite eye-opening for me. It was definitely a different approach of using modeling than those I had been exposed to at the time. And I spent many years. I haven't done this in a long time, but I spent many years, particularly in graduate school, trying to explore how agent-based modeling could help provide insight into urban systems. And some of those models I will share with you today. The software we're going to use is called NetLogo. It's a precursor for this program here called Logo Writer, which is something I used in like the 3rd or 4th grade on an old Apple computer. And the idea, as you can see in the screenshot on the right, there's a turtle, and the screenshot on the left, you give the turtle some directions. Pen down, repeat 30 times to go right turn 5 degrees, forward 5 pixels, and then you end the program and you get this semicircle. The turtle draws a semicircle. Well, NetLogo, as we see, extends this framework to not just one turtle, but many turtles, and those are our agents. It's a really robust, pretty amazing piece of open source technology, and the learning curve is quite gentle, and so that's why we're going to focus on it for this module. All right, now on to some examples. Come on. The first one we're going to start with is this Schelling model of segregation, which, as I mentioned, is a really classic agent-based model that was first conceived of by Thomas Schelling, who went on to win a Nobel Prize for this work and lots of other groundbreaking economics work. And the takeaway, the emergence, is that even a marginal preference for races of your own kind can lead to total segregation. And in this first simulation, you will see we're going to have 2 races that you see before you, green people and red people. This, incidentally, is a simulation that is in the NetLogo models library that you can, if you download NetLogo, you can play with this yourself. This is, in fact, NetLogo. So when we set this up, right now we can see that we have 20% that individuals here are looking for 20% of their neighbors to be their same race. And what's going to happen when I run the simulation is they're all going to look around themselves and ask, have they satisfied that constraint? And if not, they're going to move someplace else. So let's see what happens if only 20% similar are wanted. We run it out, and pretty quickly it converges, and we still have a pretty good mixing of races here. Let's bump it up to 30%. I want 30% of my neighbors to be my own race, and set it up, and we'll run it again. Ugh, the difference between 20 to 30 is pretty massive. You can see, to me, this is like an obvious segregation. These are clearly, these races are clearly clustered unto themselves. Let's bump it up to 50%. So I want half my neighbors to be like me, and I'll set it up and I'll go. And yet more segregation. Let's see what happens if I really bump it up here. We'll do 80%. And I really can't satisfy that constraint, it appears. I wonder if there's some organization happening here. Let me bring it down to 75%. Now we start to see some more total segregation. Before, at 80%, they just couldn't satisfy that constraint given the amount of open space there was. And now you can see there is segregation, but there's no equilibrium that has emerged because, again, the nature of the amount of open spaces. Although I have a feeling that if we let this play out, eventually some equilibrium will emerge. But the emergence here is fascinating. And it is that even a small preference for having neighbors like you, neighbors that look like you, can lead to total segregation. And this, here's an example of Professor Schelling's paper discussing this idea. This is from 1971. And of course, this is before personal computers. He was doing these experiments on a chessboard or on graph paper with, like, pennies and dimes, and showing how these dynamics worked. But obviously, Professor Schelling was way ahead of his time. And this is a great example of a simple interactions lead to complex emergent phenomena. And segregation is particularly difficult because it could be that there is this sorting pattern, this idea that people have preferences for others who live around them. But there's another reason for segregation, which of course is some sort of top-down discriminatory regime that is forcing people to live in a certain place. And really, in order to get a complete understanding of segregation, you have to understand the both sides of that coin. The preferences of individuals to sort into certain communities, and the constraints of the of institutions, of governments that may be incentivizing people to segregate. I will stop it here while these agents still haven't found the equilibrium. And I will just mention before we go on that this idea of sorting is really important if you're interested in agent-based modeling and cities, moving people, different kinds of agents across the landscape. This next simulation I will show you is what I call classroom evacuation, but it really is more about physically moving agents through space. And this was a simulation that I created years back because I had a colleague who was interested in the design of public spaces and wanted to know if an emergency happened in a particular public space, where would the bottlenecks be, and could people evacuate that public space safely? This is, as I said, a real low-hanging fruit use case for agent-based modeling, because there's a really simple behavior here, which is the agent incentive is to just get out of the room. If this classroom here, we're going to imagine there's a fire at the front of the classroom and everyone has to evacuate. Here's the exit, this green door. Everyone really has only one constraint to optimize for, which is get out as fast as possible. And so the first thing we'll tell them to do is to get out of their seat. These red triangles are our students in this lecture hall. And again, we'll watch them. I will slow this down. We'll watch them. Basically, the rule we're going to give them for evacuating is we're going to say, locate the available space, not the yellow seats, but either the white rows or the blue aisles. Locate the available space that minimizes the distance between you and the door, and then head in that direction. It seems pretty reasonable approach, right? Find the area around you that minimizes the distance to the door and walk in that direction. And let's see what happens. Let's do it again, and I'll slow it down even more. And you can see that obviously the center aisle is minimizes the distance for all of these agents. And this isn't particularly reasonable or rational behavior, right? These folks out here would clearly bounce out to these side aisles and head around. And even though these interactions are really simple, this idea that my only motivation is to get out as soon as possible, the modeler has to have better sense for what is a reasonable approach. Clearly, what's happening here is that these individuals are, what they'd be doing is trading off this shortest distance approach, bouncing out to the center aisle, with the time that it takes to get out there. Also notice that every time every turtle has a chance to move, or not, as the case may be, we tick up a turn. So this is the total number of turns it takes. And again, there's this trade-off that each of these agents is making, and it's clear that this agent should be saying that waiting in line here is not a good use of my time, and so I will give up some distance for the ability to bounce out to the side. And so a more appropriate way of doing this evacuation is not just on distance, but with distance and time, and that'll be our the other approach that we'll have to evacuate. So let me run it again. This time we'll evacuate with both distance and time. I'll explain to you what's going on here. So first of all, the darker the blue, the more traffic effectively there is. And you can see here that agents are evacuating based on where the bottlenecks are in the classroom. Now, what's crazy and strange behavior is that some of the agents appear to be bouncing back and forth, left to right, through these aisles here, and this is just the way this is programmed. They're seeing that the time and distance trade-off is decreasing depending on what moment we are in the simulation. So they're constantly changing their mind. Now, some of you may have done this if you're like leaving a theater at the end of a concert in a concert hall. You may look to the other side, to the other aisle on the other side of the seats and be like, there's no traffic there. I'm just gonna roll down this aisle and see if I can evacuate down the side quicker. And then of course you go down that aisle and all of a sudden your destination, the aisle that you chose, that clogs up, and now you've made the wrong decision apparently, and you're stuck. Well, here the agents don't have that luxury. They're constantly changing their mind and bouncing back and forth. This is the same thing if you were trying to change lanes in traffic and you realize you changed into the wrong lane. But anyway, this probably should resonate as more reasonable behavior than just by evacuating on distance and time alone. And if you have if you can model these spaces and see where the bottlenecks are, it's certainly reasonable. I hope you can appreciate, certainly reasonable to design this space in a way that may decrease the bottlenecks. So of course, that would start by having an emergency exit on either side of this lecture hall. And I'll just mention to you that if you play this out, here are 300 iterations where I'm evacuating on just distance versus distance and time. You can see that the model it's 8 times slower to evacuate just on distance than when I include the time constraint. And so it seems like a really simple, relatively simple problem where everyone has the same shared incentive just to get out of the room as quickly as possible. It leads to pretty complex behavior where this idea that at any given moment, the odds that a different route will take me out faster, there's always this change, there's always this updating of routes that might take me out faster. And it becomes a really complex problem really fast. This is an evacuation of a classroom. People build these models to evacuate entire towns and cities in the event of a natural disaster or otherwise. Moving folks through space, moving agents through space, absolutely a great use of agent-based modeling because there's this simple shared notion, simple behavior that what we're trying to optimize is to get out as soon as possible. All right, moving on. This is the last example I will give you. I think the reason that I most got interested in agent-based modeling is simple maps like this. And I kind of would look at a map like this. This is Houston, land uses in Houston. And as most of you likely know, there's no formal zoning in Houston. There are deed restrictions, which are a little bit different. And normally when people hear about zoning, they think like, oh, it must be a free-for-all. We can put all these mix up all these land uses and all these nuisance land uses with residential land uses. But it's clear that industrial and commercial land uses in Houston do not appear randomly, that they are clearly clustered. Here they are clearly clustered with respect to transportation networks. And one of my interests has been initially when I sort of started working with agent-based models years ago, I wanted to know, could I like pull the land uses off of this map and throw them randomly back on the map and give them the rules to have them kind of reconfigure themselves to where they're fixed locations on this map. And I'll show you a simulation that kind of gets at some of this. This is um, uh, a model that I call sorting of land uses. And we're going to have three different land uses: residential, commercial, and factories. And they each have different preferences for where they want to locate. So, residential, for instance, they want to be closest to commercial land uses to minimize commuting cost. They'd like to be close to other residential land uses to have some sort of neighborhood. They prefer to be farthest from factories to avoid pollution. Commercial, on the other hand, wants to be closest to other commercials for the purposes of agglomeration, because when products, the manufacturers of products, or those who sell services, when they cluster close to each other, they're able to share all kinds of inputs, not only labor and brain power, but manufacturing inputs. We call that agglomeration, and it makes it more efficient to do business. So in this instance, commercial forced to be closest to other commercial to foster agglomeration economies. They prefer to be close to residential for to provide commuting amenities, and farther again from industrial for pollution. In fact, in this simulation, I give you, the user, the opportunity to weight all of these the way they want. So what we're going to do here is we're going to start this up, and as the agents move into the simulation, what they're going to try to do is to optimize their preference, the preferences that we've sent here, and we create a variable called wealth, which is basically a function of how effective they were in locating in a place that suits their preferences. Places that have a lot of agents, residential, commercial, or industrial agents that have satisfied their preferences will have more wealth. I'll show you that in a moment. But it's clear, let me hide the turtles, it's clear that there is already some clustering of land uses. And again, there's no zoning, no top-down regime as to why this would happen. It is just these autonomous agents that are trying to optimize for their locational preferences. And you can see there's some definite clustering that's happening here. I will show you, instead of visualizing the land uses, let's visualize the wealth. The darker here the grid cell, the more wealthy the area is. And so you can see, let's go back to the land uses. This big industrial area here clearly has a lot of wealth because they're unto themselves. And both the residential and the commercial in this instance were uninterested in being close to industrial. And so the places where they've managed to cluster, that also has high wealth. And now, of course, this simulation is missing a whole number of, let's run it again. This simulation is missing many other important inputs and variables, probably most notably transportation. But it just goes to show you that even without zoning, where we just have these individual, these three different land uses that are trying to optimize for some locational preference, that we still see this kind of clustering, similar to the kind of clustering we'd see in Houston. And if I was, I could actually build increasing complexity into this model. I could bring transportation in. Here, there just appears to be such, in this instance, like this near infinite demand for industrial products. So there's far more in industry than there is residential or commercial. But we could build in dynamics that are more realistic to supply and demand in a region, to have the industry and the land use mix that we might expect. We could continue to complicate this simulation until the point where, when we press play, maybe it would look like an actual region or an actual city. And if we could develop a simulation that did resemble an actual city, well, that's an amazing sandbox that we have to play in. We can introduce all sorts of interventions and see what happens and see what the result is when we press play on the simulation. And that's the ultimate goal, is to be able to have a simulation that appropriately models society in such a way that it's a petri dish that we can run experiments. And that is the dream. So this last model I want to show you is um, around disease transmission, and it's one we'll focus on a lot in this and over the next few weeks in this agent-based modeling module, because, and it's not just the time we live in today, disease transmission is absolutely a low-hanging fruit use case for agent-based modeling. And in this module next week, I'll actually have you learn the code to replicate this model as a first agent-based model. But it's very simple. And again, the reason this works so well is because the agent behaviors are super simple. So zombies, their only motivation is to eat as much brains as possible. Humans, their only motivation is not to get their brains eaten. Seems pretty reasonable. The behavior is as follows. So the first agent type, zombies, they walk around until they locate a human in their vicinity. They face that human and they walk towards that human at speed S. If the zombie catches up to the human, it eats its brains and converts that human to a zombie. Conversely, the humans, if there are any zombies around them, they turn 180 degrees away from that zombie and they walk at speed 2S. So they can walk twice as fast, the humans can. They can walk twice as fast as the zombies. And so it goes fast. So well, let's run it and we'll see what the emergence is. So, all right. Pretty much very quickly, the zombies took over. We'll run it again. There we have it again. Very quickly again, the zombies took over. Let's slow it down so we can see what happens. Again, it's kind of crazy that it happens this way because again, the humans run twice as fast. You would think that this one zombie would never catch up to a human if all the humans can run away. And I think it's probably dumb luck that the zombie manages to catch the first human. But when it does, something kind of amazing happens. Let's see if we can catch it at a time where there's only a couple. Ah. And that time, the disease transmission was fell off a cliff. Let's try it again. I really want to catch it at the right time. So you can look at the behavior of the humans when there's a handful of zombies. But it's clear once there's one zombie, the transmission of the disease through the human population is super fast, lightning fast. Still got one. I missed it again. Well, for the purpose of demonstration, it's really important. Let me try one more time to see if I can nail it. All right. Oh, I pressed the wrong button that time. This is going great. All right, here we have two. And now you can see that the zombies kind of create these pockets of human beings that retreat in all directions away from the zombie. I'd like to get a handful more. Now we have three. You can see the transmission rate. Pretty gentle curve at this point. There are 4 zombies. Scratch that, make that 5 zombies. All right, we got a couple more now, and you can begin to see what's happening. The humans are being sort of corralled into bunches together. You can see this bunch here and this bunch here. And they basically get backed up against each other, and there's really no way to escape, despite the fact they can run twice as fast. And again, you can see the transmission rate still increasing pretty slowly. It's starting to get a little steeper more. All right, now you can start to see where it's getting exponential. We've got a fair amount of zombies. They've hollowed out the middle of the game board, and they're really hurting the humans. This board works like Pac-Man, so if they leave the bottom of the simulation, they can come back on the top. Let's keep it moving. All right, it's about to be a free for all. You can see the transmission rate, and now you can really see the humans being herded into piles, effectively. The zombies are pretty stupid. Like these zombies out here, there's no one in their immediate vicinity, so they're just wandering randomly around. And in short order, all of the humans will be gone. And you just like that Washington Post data visualization I showed you, this is really fertile ground for agent modeling because the rules are pretty simple. And you could, in theory, if you could model what the transmission behavior was, you could simulate what it's like moving agents through not only through a flat plane, but through a neighborhood, through a grocery store, through a subway system or a transit system. And you can really try to understand where some of these interactions with disease transmission happens. So we talked about really two, I think, important concepts about examples where agent-based modeling is important in urban systems. One is for sorting across places, given some economic or social preferences, segregation and sorting of land uses. And another is as simply moving through space, whether those are humans in a public space, like a park or a classroom, or cars through a transportation grid, also fertile ground for agent-based modeling. And those interactions of those agents can lead to very simple interactions, can lead to really interesting and complex emergence, like disease transmission. So some thoughts about when to use agent-based modeling versus when not to. And this is just my experience thinking about the usefulness of this technology for planning and public policy. So when the agents have a real limited choice set is one way to think about where this is appropriate. So there are lots of instances where humans have lots of choices, and they make those choices sometimes not based on the best information, or sometimes irrationally, despite the fact they have good information. And the more of that noise can enter into the decision making, the harder it is to model. So a great example is like, a national housing market where you have multiple agents. You have, home buyers and renters. You have all the way up through giant institutions like banks and governments. There's a tremendous amount of interaction and behavior that happens there. That's a really difficult system to model. And you can see in the models that I've shown you that it's really reliant on simple behaviors. And the last thing I would mention is this is also really important if you don't have outcomes that would work well in a top-down setting. So when we built the flood inundation predictive model, we started with outcomes about flood inundation training data, and the goal was to try to model the flood inundation to see if we can come up with a generalizable model that we could then use to predict flood inundation in a city that's yet to experience a flood. Well, if we have relevant outcome data, in my experience, it tends to be a better top-down, regression centric approach tends to be a better one than agent-based modeling. But the place that I do think is really important is for learning, and not just in a setting like this, but for when you are thinking about the kinds of urban problems that you are interested in. I often feel like this phase will be really helpful when a lot of planners or public policy folks are working on one particular problem. Just step back and say, who are the agents involved? And we're going to do this exercise. We're going to talk about a gentrification model in a couple weeks. We'll actually think about all of the stakeholders that play a role in local housing markets. No matter what it is, think about who the agents are involved. What are they optimizing for? And oftentimes you'll come to the conclusion like, man, there's too many stakeholders, there's too many strange behaviors going on here. But if they are few stakeholders with relatively simple behaviors and interactions, then an agent-based model may be a really interesting approach, again, to try to create a petri dish that you can experiment with different kinds of interventions. All right, so you're going to get from me a link to a Google presentation, and I'd like you to start thinking about this over the next week or week and a half by coming up with a simulation that you think is interesting. It could be anything you think of. It can be complicated, it can be simple, and I'd like you to fill out a flashcard like this for your own simulation. Give me a basic description of the interactions you want to model. Tell me about the environment. Tell me about the agents and what their motivations are. Tell me what you think the emergent phenomena is, why it's important for planning and policy, and where you perceive some of the problems might be with this model right off the bat. And this will help you to think about modeling from an agent's perspective, getting in the head of an agent. We'll have a conversation about this when we all video conference in class together. So please start thinking about this. The next thing I would like to do is to show you a quick demo of NetLogo. You can download NetLogo. It's freely available on the web. You can do that. This is the latest version of it. And I'm going to go through some code to show you how simple this is and to show you how this platform really works. The first thing I'm going to do is I'm going to come down to this command line, and you will see that I'm on this observer tab, and I'm going to put in this line of code. Ask patches to set their P color red. Patches are the environment. It is the, you'll see more what I mean by this. And what that line of codes did was to straight up ask them to do something. And this is why this programming language is really accessible, because it's this idea that I can ask patches to do something. I can ask the turtles or the agents to do something. In this instance, I asked all of the patches to set their P color red. I can extend this by asking their patches to set P color 1 of red, blue, green. First of all, about this code, you can see after I put in ask patches, I have to, whatever I ask them has to be in brackets. And I asked them randomly to choose a color from this list, red, blue, green. That list is also in brackets. And now you can start to see you can think about this almost like a raster map, that the patches are these grid cells. They exist on a Cartesian coordinate system. And what's really interesting, similar to a geographic information system, I can right-click on one of these patches. Here is the patch, that particular patch, and I can actually identify this patch. Here is the x-coordinate, here is the y-coordinate. The color is in numeric terms. I told it to set a color in string terms, but it stores it as numeric. And eventually we'll be able to store lots of different variables inside of these attributes for each patch. Now, let me just show you, if I type in CA, it stands for clear all. And I can use the tab button to tab over to patches. And if I'm talking directly to the patches, well then I can skip the ask patches and I can just set P color red. I tend to work in the observer, so I'm going to mostly stay there. Let's do this. Let's tell the observer we want a CRT1, which stands for create one. And now we have a turtle. And in fact, let's ask the turtles to set shape turtle. And let's also ask the turtles, by the way, if you press up in the command line, you can get to your last line of code. So I'll just amend this. By the way, I will send you this whole demo, and it's a simple Word file that you can run through on your own. Ask the turtles to set their size equal to 2. Now we have a bigger turtle. Let's ask this turtle to turtles to FD1, forward 1 grid space, there it is. Let's ask this turtle to, I'm going to go over to the turtle, I'm tabbing over to the turtle tab. I'll ask this turtle to right turn 90. It makes a turn. How about we can get this turtle to teleport, move to patch 10.5, bam. How about, let's ask the turtle to put the pen down and go forward 5 spaces. Now they've drawn a line. I can then clear a drawing. I have to do this over on the Observer tab. The line goes away. Let's ask turtles to pen down, repeat 20. And what they're going to repeat is forward 1, right turn, say 22 degrees. And we have a circle. Let's clear the drawing again. And let's do this. Ask turtles to repeat 20, move to 1. All right, what did this do? 20 times I asked them to move to one of the patches, teleport to a random patch, and then draw a circle, pull the pen up, teleport then to another patch, draw a circle, do that a total of 20 times. I can be iterative here. Let's do this. Let's clear all. And we'll ask the patches to set P color to 1 of blue, red, green. There we go. And then let's, I wonder how we can figure out how many green patches there are. Let's print count patches with P color equals green. 393, you can see it printed there on in the command center, on the command line. You'll have to get, the biggest thing with the syntax that'll take some getting used to is figuring out where the brackets go. So here, whatever the attribute, in this case, patch color, that I wanted to access in the patches, I have to use the operator with. Print count patches with patch color equals green. Let me try to create, say, 200 turtles. And I will, you'll see they all just cluster on top of one another, and it patch 0, 0. Let's ask the turtles to set color black. And now you will notice that when I, here I'm not setting P color, I'm setting color. So P color refers to patch color, but just color refers to the turtle color. And then let me ask the turtles to move to 1 of patches with P color equals green. So now I only want them to be on a green one. Well, that worked. Now you can start to see we have some simple interaction between agent and their environment, moving only to the green patches. But there's a few agents who have chosen to move to the same patch. How could I get these agents to move to their own patch, so there's no multiple agents on the same green patch? And the way we can do that is we can add a second constraint. We can ask them to move to 1 of patches with P color equals green, and count turtles here equals 0. Let's see what this does. Good. Now they're all on their same patch. They're all unto themselves. Now what's interesting here is let me see what happens if I so here I've basically rerun that command, but instead of like asking the turtles to do something, I've created a temporary variable. It's temporary. We'll talk about this next week. It's a temporary variable with the operator let, and the temporary variable is simply called y. And I've said let y equal patches that are green where there are no turtles. and it tells me that there's an agent set. There are 193 of those patches, and that's basically that agent set is what I was accessing when I asked the turtles to move to those green patches with no other turtles there. Agent set is this. I just want to point out to you that we can, when we're asking turtles or patches to do something, what we're actually doing is creating these agent sets. And here in there, that agent set includes 193 patches that meet this criteria of p color equals green and count turtles here equals 0. All right, let's run our first program. You'll see. Before I do that, let me show you the settings button here. I can change the Cartesian coordinate system. I can make the min and max of the XY coordinate. I can make it. I can increase it or decrease it. I can set the patch size. But this is important. This world wraps horizontally versus world wraps vertically. I mentioned this in the context of the zombie model. This is basically set up to be Pac-Man. So if you go off one side of the screen, you come back on the other side. You can turn that on. You can turn that off. But you can set up your world here. You also have the ability to vary the speed of your simulation, which we also saw in the zombies. And then there's this, right now we're in the interface tab. There's an info tab where you can tell me all this information about your model. And there's a code tab where you can write code. And I would like to do that first. I want to create a function called toSetup. And right now, toSetup will do one thing, and that is clear all. And every function has to have an end. toSetup, clear all end. I'll come back to the interface tab. I will right click and I will start a new button, and I'm just going to call setup the function that I have in my code. And now when I press setup, it runs that function. And I can, of course, ask patches to set p color to one of red, blue, green. By the way, I can check the code, but if I had an error, if I put something up there and I tried to go back to the interface, it would say, I don't know what this is. So it tries to help you debug your code as you go. It also happens, by the way, if you press check, it will also throw that error. And there I have my world. Let me let's copy and paste what I created before. So we will create 100 turtles, and we will ask those turtles to move to green patches by themselves. Let's also ask the turtles. I'm going to try to make this a little more readable. And I urge you to think about making your code formatted in such a way, particularly when you're starting off. This will make it easier for you to understand what's going on. Hopefully you can appreciate why I've chosen to format this code like this. Oops. There we go. And now I can create another function that's really like the runtime code for my simulation. And I'm going to call that toGo. And here I'm just going to ask the turtles to make a right turn, 90 degrees, go forward 1, and then I'll ask them to do a little shimmy. Repeat 10, RT5, LT5. And so I'm going to create a new button. I'm going to have that called Go. And I'm actually going to set this one to forever because I just want them to do this forever. And let's see what they do. back and forth with their shimmy. And I can, all of these turtles, let me stop it. I mentioned that I can identify a patch. I can also identify a turtle. So if I right click on that turtle, it tells me that turtle is 91. And it tells me its breed is turtles. It tells me its size. Again, I can give it all sorts of variables here, but I could also ask turtle 91. You see it there, who is 91. Ask turtle 91 to set size 10. Boom. And so now I've issued an instruction only to one agent set, and that agent set being turtle 91. And now there's a much bigger dancer in our world. So this is just a brief introduction, obviously, to how NetLogo works. We'll spend more time on this in class, and next week we'll build the zombie simulation, and you will then have the opportunity to build your own urban simulation. And to that end, I wanted to show you one last, hopefully helpful tool for you. What I've done is I've built what I call this urban sandbox to help you. For some of you, this will be useful for building these models. So you can see here we have a city of streets and avenues. We have some land values in there. We have some land uses in there. So here I think I only have 2 land uses, green and blue, but you can add more of them. I think I have the red dots being crimes and the white X's being vacant buildings. And if you're interested in housing or neighborhood related simulations, this would be really helpful. So it gives you the ability to calculate land value as a function of all of these amenities, as many amenities you can come up with. So the example of vacancy, here is the distance to all of the vacancy. The vacant buildings are these in these white X's. And there's a surface not only for vacant, but for all of these things. So in this sandbox, there's a surface for distance to the central business district, one for distance to the avenues, which are the larger streets here, distance to vacancy, distance to crime. And I give you the opportunity to derive land value as a function of these multipliers. So here, let's look at the land value where access to the center is most important. There you go. You can see that the land value dissipates the farther you get from the center. But now let me turn down the CBD multiplier and turn up the vacancy multiplier. And let's look at the land value again. Now in this instance, places that are closer to vacants are much lower in land value. And again, if you're interested in the final simulation for this module, if you want to create something that's based on neighborhood dynamics, or housing market dynamics, you're welcome to work in the sandbox, but you don't have to. And I'll talk more about what's going on under the hood next week. All right, well, that brings us to the end of this virtual lecture. I hope you found that interesting. Again, there's real use for this technology in urban systems, but it's important that you understand the agents that you're trying to model. And if the behavior is too volatile or too complicated or too irrational, then agent-based modeling might not be the best approach. But I hope I've shown you some instances where agent-based modeling could have some real impacts, not as a research tool. I think it's an important research tool, but I mean as a public policy tool, as a tool for experimenting in a closed system. So I hope you found this to be valuable, and I hope you have a good rest of the day.